because the way covalent compounds are put together can be much more varied than ionic compounds, it becomes important for us to have a little bit more deliberate way of expressing or writing these compounds so that we know what their chemical structure really looks like. We had talked about Lewis dot structures, and for very simple small molecules, using sort of a Lewis dot structure approach to showing covalent molecules really isn't that hard, right? We can draw these dots, we can change them into a stick, but covalent molecules can get much more complex much more quickly. So we need a little bit more systematic way of approaching these. Let me just warn you in advance, this video might run just a touch longer because I'm going to go through a number of different examples to show us how to do some of these Lewis structures. One of the nice things about Lewis structures is if you are a person who really likes following a list of rules, Lewis structures follow a nice little list of rules. So let's just go through them here and then we'll see how to use them in some specific examples. So first of all, to draw a Lewis structure, number one, determine the total number of valence electrons. So think of each atom in a structure as being its own neutral atom, and how many valence electrons are there in each of those, add them all up so that we've got a total number of valence electrons to work with. Next, we're going to draw a skeleton structure using all single bonds. So just connect everything together with sticks, usually by selecting a single central atom and putting all the other ones around it. Usually the central atom is the most interesting one in the group, is how I usually think about it. So it's either the biggest element or it's the only one that there's only one of. We'll talk about a few ways of choosing that central atom as we move forward. Once we've got the skeleton structure, remember each single bond represents 2 electrons, and we counted up all of our valence electrons. So then we'll distribute the remaining electrons by filling the octets or duets if it's hydrogen of all the peripheral atoms, all the atoms that are around the central atom. If we've got any leftover electrons, once those are all full, those go on the central atom itself. And then we need to look around, and if everything doesn't have an octet or a duet for hydrogen, we might do a little bit of electron rearrangement to form double or triple bonds instead of just all single bonds. So there are the rules. The best way to really figure these rules out is to work through some examples and see how to make these rules come to life. So let's start with methane. Let's start with CH4. I abbreviated the rules so they're a little bit less wordy here. So total number of valence electrons. Valence electrons. Carbon has 4 valence electrons. You can get that off the periodic table. Hydrogen, each of the 4 hydrogens has 1 valence electron, so there are a total of 4 valence electrons from the hydrogens. So our total number of valence electrons is 8. That's how many electrons we need to show in our Lewis structure. Draw a single bond skeleton. So carbon is the biggest atom here, so we'll put it in the center, and we'll draw a single bond skeleton to the hydrogens. This has used up 2, 4, 6, 8 of the valence electrons. So this used up all the valence electrons. So step 3, fill the peripheral atoms. Each hydrogen can only hold 2 electrons. So each bond is 2 electrons sharing with those hydrogens. Those are all full. Extra electrons on the central atom, we don't have those. Double or triple bonds if needed, we don't need it, right? Because each hydrogen has a duet, and the carbon has an octet, has a full octet of electrons around it. So there's a good Lewis structure of methane. What about something else? What about, let's not change it a whole lot, how about carbon tetrafluoride? So instead of CH4, CF4. Total number of valence electrons. Carbon still has 4. Now each of the 4 fluorines has 7, so we've got 28 total valence electrons from fluorine, plus 4 from the carbon, give us 32 valence electrons. I've got my single bond skeleton drawn here. 2, 4, 6, 8 electrons are already shown. Now let's fill the peripheral atoms with with electrons. So each fluorine now has 8 electrons around it. And how many have I used up now? I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I've used up 32 valence electrons. So I have no extra electrons for the central atom. And everything has an octet, so I don't need any double or triple bonds. All right, doing good on these examples. Let's move on to something a little bit more interesting. What about ammonia, one of those common name molecules that we work with? Same process, total number of valence electrons. Nitrogen has 5 valence electrons. Again, look at that on the periodic table. Each of the 3 hydrogens has 1, so that's 8, or that's 3 valence electrons from hydrogen for a total of 8 for the whole molecule. Draw a single bond skeleton, 2, 4, 6 to the 3 hydrogens. That means that I've got, well, let's see, number 3, fill the peripheral atoms. Hydrogens are all full. I've got 2 extra electrons, so I'm going to put those on the central atom and form double or triple bonds. Well, again, everything either has a duet for hydrogen or an octet for nitrogen, so we don't need any double or triple bonds here. Another example, how about carbon dioxide, another one that we talked about in our nomenclature. Total number of valence electrons. I've got 1 carbon, 4 valence electrons. I've got 2 oxygens, each with 6 valence electrons for a total of 12. Add those up, I've got 16 valence electrons available for my structure. Draw a single bond skeleton. I've used up 4 of those orbitals, or 4 of those, electrons. And now fill the peripheral atoms. I can fill the peripheral atoms, 2, 4, 6, 8, 10, 12, 14, 16. I've used up all the valence electrons. Extra electrons on the central atom. I don't have any of those, so I don't have anything for the central atom. And 5, form double or triple bonds if needed. Well, oxygen has 8 electrons, has a full valence shell in this structure, but carbon only has 4. So carbon doesn't have a full valence shell, but what if I take these 2 electrons and I bring them in and I make that a double bond? And what if I take these 2 electrons and I bring them in and I make that a double bond? Well, then I get this structure, and now oxygen still has 8. Oxygen still has 8. Carbon now also has 8 electrons around it. So this is a better Lewis structure. This is a good Lewis structure for carbon dioxide. All right, let's go even farther. What about a carbonate ion? Now we're not dealing with a neutral molecule. Now we're dealing with one of those polyatomic ions. So count up the valence electrons. 1 carbon has 4 valence electrons. 3 oxygens each have 6, so that's 18. And now what about that charge? This -2 charge means that we've got 2 extra electrons, right? Electrons are negatively charged. So a -2 charge here means we've got 2 extra valence electrons floating around in this molecule. So 4 plus 2 plus 18 is 24 total valence electrons. I've already drawn my single bond skeleton, so 2, 4, 6. What if I fill that, fill those peripheral atoms? So what do we have? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all the valence electrons. Good. But carbon does not have an octet. Carbon does not have a full valence shell. So just like with carbon dioxide, I'm going to grab a pair of electrons and I'm going to bring those electrons in to form a double bond. And that'll give us something that looks like this. all the oxygen now have an octet, and the carbon has an octet as well. So there's a good Lewis structure for carbonate ion. Now looking at that structure, I could have made this double bond on any of these three, right? I just kind of picked this one. And to be honest, I picked this one because I knew that was my next picture. But I could have made my double bond down here, and it would have been really the same molecule. So what happens when we've got situations like this? Well, if I look at those carbonates, we have something called resonance structures. If you've got a structure with a double or a triple bond that can be drawn equivalently in more than one spot, then we've got something called resonance structure. So here's the one that we used, but this one is equally valid. This one is equally valid. And in fact, probably the more real picture of this is that all three of these exist and interchange so fast that it's not really distinguishable that one of these is a double bond and one of these is and two of them are single bonds. So when we're looking at a carbonate ions actually behave as if these are all the same bond, a little bit more than a single bond, but not all the way up to a double bond. We're going to see a lot of things with resonance throughout many parts of the course. One important point when we see resonance is, in general, if we can draw multiple resonance structures, it tends to stabilize the overall structure that we're working with. We're going to have a lot of opportunity to look at Lewis structures, and we're going to continue to look at those Lewis structures. So take opportunities to practice whenever you can, and I'll see you next time.